In the first part of this little series of videos about the area of a circle and the Fundamental Theorem of Calculus, we showed that the derivative of the area of a circle is the circumference. And we did it strictly through the geometry of the circle. If you extend the radius by a little bit, delta r, then you add some new area, this green ring, and that new area, if the ring is thin enough, the new area is pretty close to the circumference times the change in radius. And this allowed us to conclude that the rate of change of the area with respect to the radius, the derivative, is equal to the circumference. In other words, the additional area added to a circle per unit of additional radius is the circumference. And that allowed us to think of the circle as made up of longer and longer, extremely thin pieces of string, the circumferences, all wrapped concentrically around each other. And we said we're going to use that, in fact we are going to use that here to figure out the area of the circle. Let's go back and look at these basic formulas, the ones we call the formulas for the circumference and the area of the circle. That's kind of a misnomer. These formulas are very, very different animals. This one, it's not really the formula for the circumference of the circle in terms of the radius. What it really is the definition of pi. Let me rewrite it just a little bit here. You know that 2 times r is the diameter. This is another way to think of it. C equals pi d. And what is this saying to us? What it's saying is that the ratio of the circumference to the diameter for a circle is always the same. People figured this out thousands of years ago. If I take a circle and measure the circumference versus diameter, and I take any other circle and make the measurement of the circumference versus the diameter, it's always the same. In other words, if I take a circle and double the diameter, I'll double the circumference. That makes perfect sense. I mean, think about a square. If I take a square and double the side, that doubles the perimeter. If I take an equilateral triangle and I double the side, that doubles the perimeter. Right? So the ratio is always the same. People have known that for a long time. But for square, it's pretty nice. The ratio of a square, the perimeter to the side, p equals 4s. For an equilateral triangle, the ratio of the perimeter to the side is 3. For circle, it just didn't turn out to be a nice number. It would have been great if it was 3.5, but it turns out this ratio here was a number we never heard of before. So we gave it a new name. We called it pi. I mean, you learned in school that pi is sort of close to 22/7, or you also learned that it's close to 3.14, but it's actually neither of those. Pi is an infinite, non-repeating decimal. Here's the beginning of it, so on, keeps going forever. There's nothing mystical about that. There are a lot of numbers that are these so-called irrational numbers. Not that they're crazy or anything, just means that they're not the ratio of 2 whole numbers. In other words, they're not a fraction. There are lots of numbers which are not fractions, and pi is one of them. So that's why we gave it a new name. So again, that's what this formula is. It expresses for us the definition of pi. It's the ratio of the circumference of a circle to the diameter. The second formula, though, is really different. Why does pi show up again here? Why should this crazy number pi show up in the area formula? Well, it's because the area formula really is this. If I rewrite it as pi r times r squared, r times r, pi r is half of the circumference. So this is the area formula. Look, it's like a rectangle. The area of the rectangle is length times the width. The area of a triangle is 1/2 the height times the base. This is a very similar thing. The area of a circle is 1/2 the circumference times r. And if we take this definition of pi and stick it in here, that's where we get the pi r squared. But this is what we want to show, that the area is actually 1/2 the circumference times r, and that's what we're going to turn to next. So how are we going to do that? We said before that it was profitable to think of the circle as a bunch of circumferences all built up bigger and bigger and bigger. And that's the way we'll analyze the circle so we can think about the area. So let's pretend we broke up the circle into lots and lots of concentric rings. Look, I've only drawn 6 or 8 so you can see them, but the idea is to think as very, very skinny rings. And so the width of each one, if I've drawn n rings, the width of each one is r over n. Think of n as very big, so r over n is very small. That's the radius. Sorry, that's the width of each one of these rings. So the idea is we're going to calculate the area of each of the rings and then add them all up, and that'll give us the area of the circle. Well, we already said how we're going to calculate, or how to calculate the area of a very thin ring. It's just this. The area of a ring is the circumference of the ring times the width of the ring. If the ring is very thin, the circumference of the ring times the width. What do I mean by the kth ring? Well, I'm just taking a typical one, right? The first ring, second ring, third ring, so on. Kth ring, somewhere in the middle. The area of the kth ring is the circumference of the ring times the width of the ring. So let's see if we can work that out a little bit. The width of the ring, we already said that's R over N. The circumference of the ring, well, it's the circumference of a circle, so it's just 2 pi times the radius. 2 pi times the radius of that circle times the width, Rn, circumference 2 pi r. Now how about the radius? Well, in the very first circle here, the radius is r over n. In the second circle, it's 2 times r over n, 3 times r over n. So by the time you get up to the kth one, it's k times r over n. That's the radius, 2 pi k. A little bit of algebra here. We can simplify r squared n squared, right? R squared n squared. Okay, so that's the area of the kth ring. Let's just put that on top so we can save it, make some room down here. And so that's the area of the kth ring. We want to add those all up. The area of the whole circle is going to be, do you know the symbol, the sum? Here we are. The area of the kth ring is this, so we're going to add them up. That's all this says. K equals 1, 2, 3, 4, all the way up to n. Now look, the rest of this calculation gets a little gnarly. I've actually made a separate video as an appendix to this series to show you how it works in detail. Let me just show you the whole thing. And here's what I want you to get out of it. Look, it's complicated. It is complicated, no question about it. But it's just algebra. It's just a bunch of algebra here. At the end, we take a limit, and lo and behold, we wind up with pi r squared. That's what it is. So we've actually shown here, by using this methodology of thinking of the circle as breaking up into very, very thin rings, that we can do a bit of complicated stuff, but not too bad, and wind up with the area of the circle. Yeah, you feeling a little nervous at this point? Why does it have to be so complicated? Wait, there's an easier way. And that's what I want to show you next, and I'll explain to you why I showed you the hard way first.